expansion to get terms in effective action. There were some technical problems which have been overcome in the recent past. And they could potentially have all kinds of useful directions to follow. So I'll just tell you what is going to do. So first, of course, I'll just tell you a couple of few words about why it's important to understand string amplitudes, because you want to get finite answers in a not a valid finite theory of gravity. And also, we also want to be contact with string dualities, because string dualities, particularly non-perturbative dualities, often you use the supersymmetry or other conjectures to make statements. It's good to actually have proofs of the statements based on perturbative string amplitudes. Now, tree-level amplitudes, more or less are well understood. I'll show you where not that well understood, but of course, I'm showing you in a minute. So I'll be looking at short my talk. For simplicity, oriented closed string theory. So T-oriented topological expansion, global shape topological expansion, there's only one diagram. So in precise case, one loop is really just a torus, nothing. And so again, for simplicity, I'll be looking at D equals 10 only. You can generalize to a lower dimension, but it gets more and more technical, and this will be enough. Okay. And then further, I'll be looking at maximal supersymmetry. So I'll be looking at A, like to be in flat 10-dimensional space, one loop. And I'm looking at the most canonical and well-studied one, which is the 4 graviton amplitude. And towards the end, I should come to also the 5 graviton amplitude, where conceptually new things come compared to the 4 graviton amplitude.
So this is the R to the 4. This is the term that gives rise to the R to the 4.
Exactly. So the low momentum expansion here will give you terms of the form e to the 2k up to the 4th. I'm being schematic here. This is essentially 2k bars of the derivative here, which in momentum space essentially, is when you write down think in terms of the Manhattan variables, ST and U, it's essentially equals k bars of course. And R to the 4 is some complicated space-time combination of this one fraction. That won't be relevant. The important thing is what is the coefficient.
Sorry, I should perhaps know this, but there are various possible contractions in the R to the 4, right?
Right. One is fixed space string perturbation.
So only one appears up the field with different spaces.
And this is the thing that in 2B theory was part of the first term where there is an instanton sum and so on, right?
Yeah, up to the 4 exactly. Up to the 4 exactly. This is a tree-level one loop and a d-instanton contribution in.
And that has a nice transformation under ST value.
Right.
So this is the green cup for
Right.
This is J function.
No, this is E3 halves. J function is purely homomorphic. I see.
No, but what I mean is when you start including higher derivatives, it's still that particular combination.
Exactly. And
this is more
this is
power.
scalar by itself, and this is a scalar by itself. So, and I just write down the answers to be clear. It's not obvious that it has to reproduce itself at every genus. So first I'll quickly review the tree level. This is well known, but I just want to write down certain terms because I want to compare and contrast with one loop. So this is tree level 4 gravity. This is just on the spheres. So exactly 4 gravity spheres. And my convention will be that all the momenta are either incoming or all outgoing. So sum over ki is the same.
Sorry, just orientation. Just the plane R to the 4 is an integral over half of superspace.
Right.
And the ones with more derivatives are.
Yeah, D4 is half. D4 is quarter VPS. D6 is 1/8 PPS. D8 onwards is nothing. So for D8 onwards, the answer is nothing. Apart from this. So the tree level again, I'll be dropping various overall factors. So tree level amplitude is the following. So you can so e to the minus 2 pi, and then this is the dilaton part, and the final answer is then minus alpha prime s minus alpha prime u. I should mention s is minus k1 plus k2 squared, e is minus k1 plus k4 squared, e is minus k1 plus k3 squared. And all the gravitons are on shift. First put this formula by gamma 1 plus alpha prime s 1 plus alpha prime 1 plus alpha prime u. And here is something schematically R to the 4. Essentially, you work at a linearized level with your scattering amplitude. So there are 4 parts of the polarization tensor and 8 parts of the moment, which actually can Lorentz covariantize and write in terms of R to the 4. So this space-time transform structure is not very important. But now you see everything factorizes. So the t to the k is 2k, that is a tree level from scalar space. So let me write down the answer when you expand. Okay. There is an expansion in small alpha prime, and I'll write down the answer. You get 1 by u plus this thing.
continue.
Yeah, up to factors of transcendentality 0. This is the answer. And this is supposed to be if you have correct combination. That's all that. So the point is, this is r to the 4 by STU. This is really coming from supergravity. Basically, 2 derivative gravity plus 4 formula differential. And these are the poles. Because in a string level amplitude pole, you have poles. This is the first contact term. It's up to the 4. So the effective action, this comes from something like this. This term comes from 3 level amplitudes. Zeta 3 actually gives you up to the 4. This one, zeta 5 gives you.
Sorry, that zeta 3 is tree level, is it?
All are 3 levels. All are 3
tree
levels.
level, of course. Sorry.
But they're making a momentary expansion.
So that's the content.
No, but what I meant was the first term is graviton exchange itself.
Exactly. It's from supergravity. You just take root GR.
Okay, it's
Plus the supersymmetric compression, 2 derivative 4 fermions. This is all that you will do. And this is a genuine contact interaction. We're going to drop because we have to separate the poles from supergravity.
Sorry, I should know this, but like if you've got a tree-level exchange of a graviton, I can imagine getting a 1 over S or 1 over T or 1 over U. Trying to get STU in the same factor. Or you just take them sort of, I see. So the
You have to use the S plus equal to
I
0.
see.
You have to.
Yeah,
And that is the only one which is consistent with dimensionality. And
you
this
just
is
add them up, basically. Then take the denominator common or whatever's left is the
and it has to be symmetric because of the two atoms. And so this is the first contact interaction. This is in half BPS. Then you have d to the 4 up to the 4. This is quarter BPS. Then you have this is the 6 up to the 4. This is 1 8 BPS. Then you have non-BPS interaction. This is 8 7. 6 8 4. Then you have 7 10 R4 plus dot. And these are fixed transcendental. This is transcendental in 3, 5. Sorry. This one is next one is vanishing because d square r4 is 0 because d square is s plus 2 plus 8 is 0. Using on show. So this is transcendental in 3, then 5, 6, 7, and so on. And it turns out that the ratio is such that it's always odd zero function. So it's very easy to remember. So the point is, I'm going to tell you what kind of numbers do you get when you integral over at 1. What the corrections are. So, okay, so a few more things to put things in perspective for the tree level amplitude. The point is, things are not so simple when you go to higher gravitons. This is a whole bunch of useful implications.
Your definition of transcendentality is the same as counting powers of pi, or is it?
Exactly. Counting powers of pi. So zeta k and pi to the k. So for the zeta 2 is pi squared by 6.
I was trying to not ask that question.
No.
Okay, thank you.
And so let me ask a stupid question. If you wrote the scattering amplitude as a sum over poles, then the first term would come from would have a contribution from graviton pole exchange plus other stuff.
Only massless pole exchange because I'm writing on effective action with only massless division.
But if I wrote it just as sum over S channel poles,
Right.
that would have the graviton S channel exchange, but plus some other stuff that would eventually.
Plus all massless pole exchange. Yeah. It would do something like this. Yes, it's a pole exchange something like this. So the propagator is 1 by k squared. It's from the root gr, each vertex is k squared. So whole thing actually has a k squared. So this is what, and r to the 4 is 8 derivatives, 1 by s2 are 6 derivatives. So that's the k squared.
Wait, so something I'm sorry, something like this can have a 1 over s, but unless you sum an infinite number of other things, cannot have a 1 over t. Right?
But there will be p channel also. Then you sum over all this thing. But this is what you get.
No, but I'm saying suppose we take this Virasoro-Shapiro amplitude and write it as a sum over S channel.
Right.
Just S channel. I want to know from that point of view the genesis of each of the terms you are talking about. That's very complicated.
Exactly.
So you can't think of it.
Exactly. If it's only external, it will
I was just wondering whether you could identify what some linear combination of these sums that seem protected because they're related to supersymmetric quantities.
So up to this, d to the 6 up to the 4 is correct.
Right, but if you wrote it in terms of the sum over S channel poles, it seems like it's summing over an infinite number of things.
Right.
The things that summing over are not supersymmetric, since there are no supersymmetric oscillators other than, well,
that's true.
other than the muscles things. And yet their sum is producing something supersymmetrical.
Yeah, but when an infinite sum is kind of hard to, kind of.
I understand. I was
Yeah.
just wondering whether there was something special about part of the sum that gave rise to the supersymmetric thing,
Right.
because it was protected. But
Yeah, it's very difficult to say because the supersymmetric is not very easy to say when you actually have this manifest STU duality. So.
I was wondering whether, something like about the growth and density of states, or something very particular about energy behavior, fixed, this fixed,
Yeah. I say the fixed test last is kind of.
something like that, something nice should fix it.
Yeah. That at least I don't know. Well, yeah, I don't know if it helps anything. Yes, but one more thing before I go on to tree, I look at the structure, gets much more richer when you go to higher part function even at tree level. And this is probably a lot of interesting questions, so I just want to make a comment. That here we got Riemann zeta functions. Essentially, zeta of S is defined as 1 by S, so n. And S can be a complex number, real S has to be greater than 1. When you look at higher part amplitudes, you also get what are called multi-zeta values, NZ. As I mentioned, and there's an interesting issue which comes up because so multi-zeta values are defined as, I just defined it as simple case, say zeta SR would be 1 by n1 to the S into the R. Sum over all n1 into what n1 has to be greater than 2. This comes. In tree-level string amplitudes, in gravitons as well as tree-level.
So if you want to get 5 point or 6 point,
I just come to that. So then it becomes interesting, and multi-zeta values you get a whole bunch of things. S1 to Sk, and even obviously graded sum. So these are interesting because the question is, how many of them are independent? Given a fixed transcendentality, how many of them are independent? So I'll just write down the answer for some of the first ones to show you what is it. It is only for the 4-point amplitude that things get very lucky and you get very compact ones. But even to the 5 graviton amplitude. So let me quickly write on a table for you to see how many of them. So this is going to be my transcendentality. And I just write down the basis. So when the transcendentality is 0, we just have just 1, so the genius is 1. There is no zeta function. When the transcendentality is 1, there is nothing because zeta 1 is divergent. So it's really 0. So let me write it down up to that order because I want to show you something that the first transcendentality 2, so this is just zeta 2. So it's just 1. Transcendentality 3, zeta 3, that's 1. Transcendentality 4.
now you have more.
No, zeta 2 square is still, I'll come to that.
Oh, zeta 4?
So zeta 4 is pi to the 4 by 90. Zeta 2 square is pi to the 5 by 36. So the ratio is.
Oh, okay, I see.
So even zeta is always pi to the 2. Right, zeta 2 is pi to the 2.
I see.
The rules are that you're allowed to take only linear combinations that have no pi's.
Exactly. So when you go to 5, something different happens. You actually get 2 here for the first time because you have zeta 5 and zeta 2, zeta 3.
So zeta 3 start is like what, pi cube? Is
No.
it?
Odd zetas are not pi.
All zetas are not pi.
It's only the even zeta. Odd zetas are not pi. It's a new transcendental function apart from pi. So far as I know, no one has ever proved that zeta 5 is transcendental. The proof ends at zeta 3.
So that means zeta 2 has a pi in it, but
Yes.
zeta 5, this guy does not have a pi in it.
This guy does not have pi. This is actually pi square zeta. That's why they are thinking.
So, how do you define then?
Yeah,
Transcendentality means what exactly?
Yeah, that's what I was going to ask.
This-
Yeah, I thought you were counting
It's also about transcendentality. The operation is also about weight. Okay, zeta k has weight.
That's why it's difficult.
By
Here you could have put a pi cube also. Those are trivial ones. I'm not writing down the ones which are only pi.
No, but what I'm asking is, okay, is by some definition you may say zeta 5 has weight 5. But why does zeta 2 times zeta 3 also have weight 5?
Because this is the sum of these weights.
Oh, just by definition.
Just by definition. Alright. So I'll write down a couple more. So zeta 6 actually has 3 squared and 2 cubed. So it has 2. 7. And zeta 7 is 5, 2 square 3, this is degeneracy 3, and zeta 8, sorry, weight 8 is the first time actually you get a multi-zeta set. That's why I'm writing in this table. This is zeta 2 to the 4th of against 1, zeta 2, zeta 3 square, zeta 3, zeta 5, and zeta 3 comma 5. So this one cannot be written in terms of Riemann zeta function. This was the first thing. And this actually doesn't appear in closed string theory, it appears in open string theory. The one amplitude is the disk point function actually has. And the fact that there's nothing below this is a non-trivial fact in acquisition. For example, if you look at say transcendentality 3, you could have had zeta 1, 2. No, stop.
Out of view that.
Oh, I'm sorry. Yeah, this is the line. So transcendentality 3 could have had zeta 1, 2. It turns out that zeta 3 is equal to 2 zeta 1, 2. Exactly, which is something modular 2.
By the way, I don't think there's anybody in ICTS. I'm just saying because if that's the case, he may as well use the Facebook.
Yeah, and our camera has full.
No.
No?
Camera.
No, currently camera only has.
Oh, I see. So you're saying just for filming purposes. Okay, okay.
Yeah, so this was actually proved by Euler in long term. That zeta 1 is actually equal to zeta 3. So there's going to be a new element of the basis below transcendentality 8. And one more, let me give an example. What happens at transcendentality 4? We are actually, again, it's just degeneracy is 1 because zeta 4 is equal to zeta 1 over 2, zeta 4, zeta 1, 3, zeta 4, zeta 2 is equal to. So the highly non-trivial relation which tells me that the degeneracy is much less. Okay, these have been proved. So the question is, okay, so for the open string theory, this is the simplest multi-zeta value which comes out. For closed string theory, the simplest multi-zeta value which comes out is actually zeta 335, which is transcendental gain. It actually comes out in a this fact in which it really is a equal to 14 part to the 5 amplitude actually exist. The first case where multi-zeta value arises in closed string.
So just let me continue to ask stupid questions. Why is it seems like there is some rule that the higher the number of derivatives, the higher the transcendentality. Why is that the case? Or even roughly, so there's some way of
Yeah, I see. I mean, you got an increase in the power of these guys when you go to, which is essentially when you do the calculation, this is how it comes.
I see. But is it a general theorem? Is that
No, because
there's
even when you go to non-previous interactions, even at a fixed order in alpha prime expansion, always the transcendentality doesn't stay the same. It just happens for some simple reason. Now, so you see, this is all that I have to tell you about tree amplitude. Now, the question is, it all looks very nice and kind of complete, but what can you say about blue band? So that's what is going to be the main focus. Is there an angle of some simplification in loop amplitudes? Because whether you can simplify it or not, but we have to do the calculation at the end. So it helps to have some simplification.
Sorry, what was the lesson from this table?
So there's a huge simplification in the basis, like given a fixed transcendentality.
The number of terms that you might have got.
In fact, I think it was originally conjectured by Zagier that if you look at the degeneracy, if I define it as dn, something you can write a genetic function that dn t to the n equals 0 to infinity, that's simple as whatever. So there's no order t term because zeta 1 is diagonal. This was conjectured by Zagier and proved.
What is the symbol? Sorry.
Yeah, dn is a degeneracy.
Number of
degeneracy.
Yeah, number, yeah.
Yes,
It's
so
supposed to be
1
exact.
minus t square minus t cube.
There's no order t term because zeta 1 was diagonal. So you will say t1 is 0.
And this matches your table.
Yep.
It matches the existence of that last one in terms of
This was conjectured by Zagier.
There's some intuition for this is.
I don't know the proof, but this is. But important thing is the same, there's a lot of simplification also, a lot of nice mathematical identities also will come out. And particularly beyond tree level, variability is more.
But this sounds like it's saying that everything is produced from zeta 2 and zeta 3.
No, there's a zeta 5 range, for example.
Oh, because they're cross terms. Yes, I think. Yeah.
So,
Yeah. And under 1 minus t squared into 1 minus t cubed, then it would have been everything is produced from
exactly. So there are very many reasons to try to the fundamental nobody is going to be the standard definition. Let me quickly draw it once and for all. This is 1 and this is R. This is my fundamental. I'll stick to this. So the one loop amplitude is typically of this form. D2 tau by tau 2 square over this fundamental domain. Of some function of tau, tau bar, and the external momentum. And there's going to be some operator, which is going to be KI and some various things. So this is the integral 1 is 2. So now one has to be careful over to, there's an apparent divergences, whichever is being interpretation, one has to be careful about how to do.
What are the phi i's?
Phi is some fields. For example, this will be 4 gravitons.
The polar.
Polarization is.
Yeah, polarization or whatever. I mean, yeah.
Okay.
So this would be the up to the 4 gravitons. This is a generic. So all I'm saying, this is independent. I mean, this we don't have to worry about. You can forget it. For that purpose, all we have to do is this integral. Now the point is, there's one potential kind of divergence which comes out. It also comes out in the tree level, which is essentially when you are doing this integral of the vertex operators when vertex operators collide. They have the same. Right? So this is an interpretation in terms of so when two of them come together, it's really a massless pole. So the poles have to be subtracted, and which is a neglect because I want to look at contact interactions. So this arises even at tree level, and this was informed 1 by ST. And the another thing is, from the boundary of modular space in this convention, which is down to going to infinity, there will be another source of non-analytic terms. So those are non-analytic terms. They are dimension dependent. They can be divergent or not depending on the dimension. So those also I have to kind of essentially ignore because I want to look at contact. So these are two things I must look at. So how do I get rid of this? So the point is for these two guys, I really can't make an expansion in alpha prime. For this one, I just keep it, the whole expansion as it is, in STU, and just take Zi minus Zi very small and do the integral. So this can be. In particular, for the case I'll be looking at for the 4 graviton amplitude, actually there are no such terms. Because you see, for the 4 graviton amplitude, suppose there was a term like this, suppose there was a pole. It would be a diagram like this, right? Let's say one of the vertices would be one loop, another would be 3 loop. There's 4 graviton, there's only possibility. But this will know in superstring theory, 3 massless modes. One loop amplitude is vanishing. This can be, the Green-Schwarz formula, the number of zero modes in such. But for example, for the 5 graviton amplitude, there would be a term like this. So you could have had a term like this. This is one loop, this is 3 loop. Let's just show you that the one loop 4-point amplitude is not.
You think somehow that all singularities come from one shell processes?
Yes. That all the poles here. And the branch cuts and everything will come from it. For example, here, so I'm not going to talk about, but if you take the 4 graviton, you can have a diagram like this here.
So just to understand, the top thing, it sounded like you were saying that we know that there is no
For this one,
unitarity
4
touch
Exactly.
from one loop with tree.
Exactly. Only for the 4 gravity.
But that argument said that there was no unitarity pole. Couldn't there be a singularity that was not associated, not a unitarity singularity?
Yeah, you got a multi-particle cuts here. For example, there is a singularity like this. For the 4 graviton, it is known that the leading contribution is S log S R to the 4. Then the next one comes out to be S to the 4 log S R to the 4. And this one has an interpretation. What happens is, here you actually put the supergravity vertex. This one, leading one is both a supergravity vertex. Then you do two particle interacting. This one subleading is, here you put a supergravity vertex. Here you actually have the zeta 3 up to the 4, the 3 level one. So that's why it was, instead of R plus R to the 4, there were 6 derivatives enhanced. That is exactly S to S.
Just to ask again stupid question, but it seems like you're using the following theorem that all singularities that happen when two vertex operators come together are essentially unitarity singularities. That's a true theorem?
I think so, exactly. Because for the OP, that's all that you get. And all others are left, these guys, they will come on the boundary of modular. So all I have to do when I look at contact terms is to kind of remove these regions from the integration of modular space.
Yeah, but you're not an offset propagation. But I suppose you're right. Yeah. In Feynman diagram, they think this is true. Yeah.
When it comes out, but you exactly know what interpretation to take. The mistake one can make is when doing this kind of calculation, you should not expand in alpha using one particular case. But for the remaining part, the contact terms, which is from the rest of the modular space, which are genuinely contact terms, you can expand in alpha. That's what I'm doing. So that is just to set the.
And sorry, you explained this, but how are you going to cleanly separate out these?
Yeah, this is what I'm doing. For the 4 graviton numbers, which I don't have to worry about because it doesn't show up. In the 5 graviton, it shows. When you So these are cases you should not do, but what you'll see, you'll get a Green's function from the point B. So this is essentially throughout those parts.
So your procedure will give you a path which you.
This is exactly no. And in principle, you would have resampled this thing. And a string field language, theory language around this insertion actually have a epsilon disk, right? And you throw it at in the bit of single T is green actually. And this one is a little bit more complicated. So this is an analog given at tree level. This one I'm going to regularize them to right on right. So here, this one is much more involved. So here what I'm going to do is chop off this modular space by what I call FL. So insert a cutoff here. This is L distance here.
So as tau 2 goes to infinity, the things that are contributing there are essentially very low gravitons running in the loop, or just on shell.
By low grav, sorry.
Low
energy. There's no one thing.
So where we got this, and both momenta running in the loop are very low.
Although log means that you probably get contribution from all movements, right?
Yeah, it's an integral, but for the vertices you put in the massless there. So then you do the infinity cut and you get the cost you also get the imaginary part which has this thing. Integrate the fact, you get massless. So this will come to a little bit towards the end, but it's not going to be central to it.
That's a standard IR divergence from the point of view of field theory.
Exactly. And this you must reproduce in string theory.
And this is one of these collinear divergences?
I'm not sure it's collinear, I don't know.
Okay.
Also, by the way, this is dimension dependent. In lower dimension, this goes as S to the square root. So they are not IR divergence, these are either finite parts. Here is IR divergence. So this depends on dimension. This is not universal actually. So for here, what I'm going to do is cut it off at L.
It's a log divergence. Sorry, but why do you call it IR? It's IR, UV, everything. Every decade in momentum contributes.
Yeah, but for string theory, this is IR.
No, for string theory it is, but not in the...
But in supergravity, exactly. Supergravity actually, this shows up UV divergences. This is an interpolation in terms of looking at the cylinder this way or that way. This is IR divergence. Exactly. So here what I am going to do is cut off at some large value of L and take L to infinity. Okay. The important thing is this part will expand in alpha prime. There will be terms which are finite plus terms which diverge at L as L goes to infinity.
Actually, I didn't understand. Let me understand. If I put in some external momenta, there could be divergences that come only from very low momenta running the loop of momenta becoming collinear and so on. And those divergences are in principle distinct from momenta divergences that come at high momenta,
Right.
even in supergravity.
Right.
And this last part
Yes,
is the first time.
supergravity has both
Has
both higher and UV.
But they're distinct things.
They're distinct things.
And this is the IR type.
I think in supergravity, see arc to the 4 I think has a UV divergence in supergravity. Not in 10 dimension. This is exactly. I think this is generally
I think.
because supergravity in 8 dimension actually is just a box integral, the massless scalar field theory. So in 8 dimension, this is trivial d8 k by k to the 4. That's the UV divergence.
And I thought on general terms, anything happening at tau 2 equals infinity in this picture is happening at very low energies in the
Right. In the string.
So what is the conclusion? This is an IR divergence.
I'm saying in supergravity there's a UV divergence of log is in 8 dimension, not in 10 dimension.
Yeah. So this divergence is IR in supergravity.
This is IR.
Yeah.
So this is tau 2 will be.
I mean, you could have one of these log divergences that are cut off by external spectra. I think that's this side. So it's all the way down to very low energies, cut off by some momentum scale of the process.
Yeah, so here what I'm going to do is cut off the integral at large value of L and set L to infinity. So then I'll get finite parts plus parts which diverge.
Yes.
So parts which diverge, parts which vanishes and goes to infinity. So diverging parts will cancel, the other one from here to infinity, where actually don't make an expansion in this. So at the end of the day, I have to do this integral, keep only the finite terms as L goes to infinity. So that is the goal. So for this part, what I'm going to do is just expand this guy in Pazwa. And then recover contact in range. So for that I have to give you, I'll be looking at the 4 graviton and I should have to give you the expression for the 4 graviton and then I can perform this integral.
Sorry? Can you repeat why you are allowed to take only finite terms that are finite in L? Why are you allowed to take terms that are only finite in L?
Yeah, when you do this integral, there will be terms which are finite in L plus terms which diverge as L goes to infinity.
Yeah.
So terms which diverge as L actually are breaking from this thing to L and L to infinity. So terms which diverge will mutually cancel when you do this and this. So the finite parts, when I do the expansion, you will see these are contact interactions. It will be clear when I do the expansion. Because there is a finite thing here and there was this O hat, right? So this is a contact interaction. The increment of it.
But maybe to re-ask Ronald's question, that the path that comes from L to infinity will have a path that cancels this, but could also have an additional finite.
Exactly, and those will exit these parts.
Okay.
So the L dependence will cancel. There will be a finite piece from there as well, but those will be non-zero.
This is assuming that the overall amplitude is unified.
Which is that you know, simply you know. That is well known for decades. That's one thing you know for sure. The important thing is to how to. So these are actually field. I mean, these are infrared effects. These are field theory poles. Issue is how to get the contact.
Yeah.
If we find it, that is the new thing. Right? Because this in principle could have been a field theory. I mean, not difficult, but in principle it could have. So I'll write down the one loop expression then. A one loop. This is 2 pi. R the function of again h3.
And so the field theory calculation you have to do to reproduce this term, would it use just Einstein gravity or corrected Einstein gravity?
If you want to look at S log S, it's just Einstein gravity. If you look at the other one, it can correct Einstein gravity because this vertex will be zeta here.
Yeah, thanks.
So this is beyond the other terms are beyond supergravity.
Yeah.
So again, you see there's exactly this R to the 4 which comes out, and then again this is a scalar unit. So it all boils down to what I estimate. Okay, so if you write down the expression, so I is the integral over the fundamental domain, and I'm already writing down over the fundamental truncated fundamental domain because I look at contact terms, and there's an F S U function of tau and tau. So I must tell you this guy because that is all that I need. F S U tau and tau bar is in. This is integral over the positions of insertion on the version of the 4 vertex operators. Because the 4 graviton I equals 1 to 4. And essentially like a covariance for the modular amplitude. Where this is just d2z really means d real z, d imaginary z. And this the integration of the following: real z goes from minus half to plus half, and imaginary z goes from 0 to tau. So that there's a tau to here, so the integration is really 1. There was nothing. So no one has it. So all you're doing is just integrate the 4 vertex operators, one insertion to the version. And it's so simple because it's supersymmetric. Apart from this covariance and factor, the number is just 1. So I must tell you what this d guy is. So 4 by alpha prime d is really S. Okay, 1, 2, 3 and 4 the insertions of the world sheet. So S, these are the Green's functions, scalar Green's function. From 1, 2, 3 and 4. This is 1, 4. This is 2, 3. Very simple.
So, so you were using that kind of picture for each graviton vertex operator, so that is something like psi to the power I kx, so that and the psi are just saturated zero. So therefore, I mean, normally if I use del x mu plus e to the power I kx, then there will be non-trivial functions of z hanging around.
Yeah, but those they all cancel in supersymmetric because I have to have the correct picture number. Right? I need a -2.
Yeah, so I think you were just this is
So do you need del x del vertex? And for 2 is the -1 picture. So then you have the scalar side. And it's because of supersymmetry this is 1 actually. For non-supersymmetry this is far more complicated. This is really the covariance factor. I mean, this e to the and everything else cancels. For example, the heterotic string actually there are Riemann factors of eta 24. And what other complicated stuff. So this is because it's supersymmetry. That's why I'm looking at the amplitude very simple. And this is more or less all that's known in the literature. So I'll just quickly write down this G and explain why I'm calling it G hat rather than canonical G. Because the main reason was when you wrote it on the conventional way it was in the literature, I mean, very difficult to do this integral. There was only finite number. So G hat is really the Green's function a point separated by distance z. No, and this is right in terms is theta 1 tau by theta 1 prime.
So the first one is like the log of the prime form.
Exactly. This is the log of the prime form. And this is the integral of the period matrix, the imaginary part of the period. But the important is I'm going to rewrite it in a completely different way. That is the reason why this amplitude is not going to be solved. Essentially, I'm going to write on the answer is going to be written exactly the following form. This is on the bottom end. This is a very simple looking sum here. Plus the constant mode, the constant. Now see, this constant modes never matter in amplitude because s plus t plus u is 0. So I from now on only focus on this part of the equation. It is all that matters. Let's call it g. The rest of it. This is very simple. This was the reason why the amplitude now can be calculated. Just rewriting it a different way.
So this is some expression for the theta ratio.
Exactly. Essentially, this is periodic on the this is periodic on the torus. I'll just explain. Maybe write it down here. This is periodic on the both sides, and it is single value. The way of written it, g z plus 1 tau is equal to g z plus tau tau. Is all the manifest properties. This is much easier to work. That's the reason why it's done. And so now, one can take this one loop amplitude and write down the first two terms in expansion. I'll just write down the answer here. Then I'll tell you what the implications. So this is the expression here.
This is some kind of image summation, is it like this operator and this?
Well, you just take this as a convenient representation of this theta function, and you just Fourier decompose. Because it is periodic with periodicity, imagine it out in the y direction and one in the x direction.
I was just wondering whether this is the saddle point evolution of the same function integral, the same Cauchy integral that you have.
That could be, but I just got it, there's an representation of theta 1. And this is this is Fourier transform. This is originally done by Sherakin's Warner and Lerke in their Epigenius paper. Actually, they got this expression. They were really appreciated. Well, they are calculating the signal where those anomaly projected. But here's a little more. So I just basically I just write down sigma 2 is alpha pi square s square plus t square plus u square. Sigma 3 is alpha pi 2 s cube plus t cube. And one can show that everything can be written in terms of sigma 2 and sigma 3. For example, if something is s to the 4 plus t to the 4 plus u to the 4, it's proportional to sigma 2 square. That's one thing. Essentially because s plus t plus u is 0. So this is all. So I can just write down the expansion of this. So let me give you the answer. A, one loop, by 2 pi, this integral, over the truncated coordinate, the domain is 5 to the 4. This is 1, plus, I'll just explain these diagrams, and will draw it this way, just explain it, let me just draw it. This is d to the 4 after the 4, basically. D to the 6 after the 4, here I'm going to calculate factors. There are two contributions. Then, the 8. This contribution, this, and then end with due to the 10. So give you the expression. That is all. Okay. Now let me explain what this diagram is.
Is this something you can systematically continue to arbitrary or?
Arbitrary, I'll just talk about it. Arbitrary is more than technical mode. So I'll give you an equation after this. So what are this? See, when you do this integral, say f actually the integral over the 4 vertex operating expressions. Each of this is what's called a modular graph function. Now this is basically the verticality of the points 1 and 2. So a green function going from 1 to 2 and 2 to 1. This is a green function going from 3 to 4 and 4 to 3. So So each of these modular graph functions, a vertex in this graph function is a position of worldsheet operator intersection. And the link here is a worldsheet scalar intersection. They form graphs. And they're modular because they're elliptic graphs, because they all the self is elliptic. Okay. And note, you need not have to integrate to all four the vertex operators need not all four of them come into the picture. But here the two are integrated over, rest will just give you one. So the question is, how many of them are independent? Because they have a large number of them. Because in field theory, typically topologically distinct diagrams are really distinct. Here I'll show that actually this up to this order, essentially there's only one independent diagram. So, but anyway, one has to do this calculation to get this answer, because then one has to do this complicated to be integral over modular space. And these are very difficult to do.
So what do you mean by independent?
Because, for example, I'll show you that up to lower order diagrams, all these diagrams can be expressed only in terms of this. For example, this and this are related. This and this are related. This and this are related, which is not what we need in field. So essentially, like the reduction in the basis elements for multi-zeta value for a given transform. So these conjectures were already put forward by in several papers by Green, Basu, Doker, Budagon, Kaili. So I have an alternate proof for this conjecture, which is very different technique because they use much more modular properties than the integral. So these guys are what I call modular graph function integration. And if you look at them because they use holomorphic properties and also the very detailed, when you take these graphs, you can write it as an infinite sum, right? Whole bunch of integers, sets of integers here. Then you do some expansion, you can prove it. What I shall prove it using different techniques. So the details are not important, but keep in mind that there is kind of graph that comes. And one has to evaluate this graph and then integrate to the fundamental domain and find the final part.
Just say give this what one of the graphs is.
For example, when you bring down these factors here, right, the exponential of these, and you integrate the worldsheet position, this is really, this graph comes from d2 z1 by tau 2, d2 z2 by tau 2, there's a d12 square, and there's a d2 z3, d2 z4. But those are normalized to 1. This is what you get. This is between 1, 2, and 3 there are properties. This is between properties. So the graphs are actually a maximal 4 vertices because we are looking at 4 graphs. And the number of links here is essentially k in the d2 z2 capital. And the issue is to calculate them and do them.
And the g's are these g's.
What are the g's?
The green functions, your g1.
Green x, all x. So now I'll tell you how I did these calculations. So the point is the following. You can of course write it as an infinite sum here. That is, it's a bit of a mess. So it is not used. That I use a completely different way to look at it, which is the following. So the aim is the following. Of course, this is what others did also. Some of these graphs are simple, which is to write down the answer, but most of them are very complicated. But then the point, the graphs satisfy Poisson equations on modular space. And then come to toward the end of the talk, given this fact, how can you do these integrals over modular space? But first, to show what kind of Poisson equations they satisfy. Okay. And the Poisson is essentially so that I need to know the Laplacian, and the Laplacian is del. I just write it del. It's del 4 tau 2 square. This is the number. So these are supposed to be eigenfunctions of these guys with some source terms, which one is to determine. But if you just do delta over of any of these diagrams, the complicated ones, it's kind of quite messy. So there's another way to look at this, because these are actually characterizing changes in the complex structure models of the torus. One can actually express this change in the complex structure models of any Riemann surface, also in terms of Beltrami differential. So this turns out now the Beltrami differential on the torus is really 1. But its variations can be non-trivial. And this exactly turns out to be a variation with respect to the Beltrami differential mu and mu. My question is, I'm going to not write it down in the language of this torus modulus, but everything in terms of the Beltrami differential equation. And find out if they satisfy eigenfunctions of this. So for that I need to tell you how del mu and del mu bar, what you get in the Acton-Green's function. And this is a very simple elementary representation. Now this has been worked out from all genus. I'm giving the answer for genus 1. point is the following: delta mu of say the Z1, Z2 turns out to be minus 1 by pi into Z del Z of G Z1 Z del Z of G Z2 Z. So in other words, when you actually have this Green's function from 1 and 2, you actually del mu, whatever is up to a normalization, everything is integrated also. So when you're writing the integrals explicitly in the diagrams, you have really have an extra vertex over which you integrate. And similar to the complex function, which is the del bar. That's simple. And another important, very important identity is that del mu bar of G, that should be 0. Just very useful.
So just to understand, so this equality means that the change of the Green's function under an infinitesimal change of the
Following
vector
part of the vector differential
is equal to this thing times the increment of the delta.
No, that's it. That's it.
That's by definition. So
This you can work it out. In fact, given this sum, that is some expression, you can actually do this integral trivially. And this turns out to be just tau to del delta. Okay. The lattice sum is exponential, it is periodic, so it essentially given sines and cosines. So the integral can be trivially done with like this with a tau to del delta. But the point is, this hugely simplifies analysis because everything can be done in terms of Green's function. One doesn't have to worry about any modular properties of the integral, particularly the nasty expression in terms of geometry function and all. So now you see, what I'm going to do is take any of these graph functions. This is my Laplace. Act with the mu and the mu bar, and I know that mu and mu bar both cannot act on the same line. Now scatter mu and mu bar, okay? And then of course at the expense, I've got more links here, right? But the important thing, there will be certain number of derivatives in each diagram and equally number of antiderivatives, del and del bar. So the issue is, can I move them around? And using a property of Green's function, this is write down, so that they can annihilate, and you're left with the diagram which has no derivatives. And the relation I'll be using is the obvious one for a Green's function, so just write it down here. This is the following. Del Z, del bar, pi. So if you bring a Z and a Z bar on the same link, then I this one actually shows that the diagram separates, right? And this one is a 2-point become So if you can do it and systematically get rid of every del and del bar on a diagram, you are done. Or it could be that all the del and del bars cannot be removed, in which case that's the final answer. So essentially like doing electrodynamics on the numbers. So let me just then proceed. I'll be using a few more identities. One is that, because this is single value, I can freely integrate by parts without picking up anything. It's a compact word shape. Another thing is that if you just have this, okay, that actually turns out to be 0. There's nothing else which depends on Z. And then that is sum. This is contribution only from M and N both 0, which is exactly what was excluded. So it tells you you cannot have a diagram which actually ends at a point. It makes life so simple. And one can also show that one particle reducible diagram gives 0. The momentum here is 0. And torus doesn't allow. Because there is 0 mode always comes in. That S plus T plus equals 0. Okay. So that's now it's a very simple diagrammatics, and whether you can get rid of this derivatives or not is the challenge. That's the only thing.
You can move around derivative to identify diagrams.
Yeah, suppose you have a diagram here, right? And you have del on this Green's function, so nothing else. You can just move it around. This way integration.
And this helps in doing what?
Because suppose you have del and a del bar here, you bring del and del bar here. So that is an identity. And I just explain it to some diagrams. So you can remove every diagram. And hopefully at the end you will be something simple. What I do, I just prove some of these things, but all these conjectures and stands.
You get something simple for the action of del square on the graph.
Exactly. You want to get a point equation.
Yes.
With good source.
So with sources. It will automatically come out.
Well, this helps you in simplifying the source.
No, getting the full point equation. And how is exactly doing? So given a graph function, it satisfies the Poisson equation.
Yes.
So you want to act on the graph function with this. That's given axial of this. So now you sprinkle all the ways with mu and mu bars on different links.
Okay.
But mu is 2 dels.
Okay.
Mu bar is 2 del bars, so different links. So can you move them together to bring on one link? So this simplify using this.
Yeah, but whatever you get, I think Gorodao was calling the source. Because del square on that is equal to something. That something is on the source.
Well, something will be no itself plus some supersymmetry. Because it's a quasi equation.
Yeah. So del square on something is equal to something.
Yes.
That
Plus the
second
source.
The second something is what I call the source.
Yeah. See, delta of f will be something like lambda of f plus f. Is this the source?
Oh, it is square at the homogeneous addition.
Oh.
Otherwise, in the Laplace equation, it generates a quasi equation. So I'll just work out one of the simple cases and I'll give you the answer. So let me just set my notation because I just want to use diagrams. So when I have something like
And the hope is that f hat will be something lower order.
this, so there is central symmetry, but
Yeah.
it's easy.
Yeah.
So the convention is the
So
following.
it is recursively so. You saw the lower order guys first. Yeah.
So you see here points 1 and 2. If I write this way, it will mean that it is del 2 of T1. It is minus del 1 of T1. I'll just write diagrams. I'll never mention all these facts again. So that just to see the answer. So first let me tell you that some of these are very simple. I'll just write down the answer because I want to be completely more non-trivial ones. Some of these are very simple. I guess I'm going a little bit over time, but if you that's fine. If you think we should. Some of them actually.
So just to, this equation which related del tau to two insertions of del z. So is it eventually related to the fact that the theta functions satisfy a heat equation, like which makes del tau
Is it del
tau square, del z square? Because I know that it's true. I mean, in the same of the theta function, there is an e to the power minus n squared tau
Right.
plus nz. So
Right.
so it
Yeah,
actually satisfies the heat equation.
Could be, I don't know. For me, it's a trivial identity, but yeah, could be a trivial identity. So we integrate by parts, we get del square and 1 of this. That could be a trivial identity using the theta function for. So some of these graphs, which was this, and this I shall write down. This actually I need for the 5 graviton, but we mentioned it. These are very simple. I just write down the answer because I want to look at the complicated cases. They just satisfy trivially very simple Laplace equation. Here's the answer. That this guy actually is this. This is 2. Now this is really the graph and this is the Laplace. So this is 6.
Small triangle is the Laplace equation.
So I will just put this one down. This one.
So it's simple because there are no sources. It's homogeneous equation.
And it's okay. So simple isn't because you see the coordination number is always 2 in all these graphs. Modular this one. That's the reason it turned out to be simple. I mean, whenever the graphs are got spread out, they're easy. The most complicated one is this one. This is the actual result. This is coordination number here. Iterative will have 6 and so on. So it's really more easy.
And now, in order to solve these equations, you need some boundary conditions
Yes.
in tau.
So I'll write down the solution immediately. So for that, let me just give you that answer. I mean, this is non-holomorphic Eisenstein series. This is the following. This is following. Now you see why this lattice realization of the grid functions was very useful. And this is known. You can easily check that they satisfy Laplace equation. This is the fact.
Then we just pick the numbers.
Exactly. So these actually, so let me write
And
down.
these are the unique solutions obeying some appropriate boundary conditions.
That exactly. There's finite number of power wave terms that exponentially suppress the last term. So earlier what people tried to do was do these things as brute force. You will stuck. But now the knowledge is you try to find out, equations satisfied by them.
Right.
And how they can solve it will come to the right thing. But first we try to get the
Is
equation.
S called the weight of the function?
Yeah, people call it, I mean, you see, weight is supposed to be, typically people often call it for the weight of a modular form. These are all modular forms of weight Z. This is just still there.
Okay. And S has nothing to do with transcendental.
expansion, the leading term is this thing. So in some sense, yes. But they are all modular weight zero.
Okay.
Not because weight. I mean, weight is typically for the modular weight. And this is only one case given is SL2 set. If you look at SL3 and SL4, they depend on the rank. So we are lucky here is SL2. So then give you the answer then, just for this guy.
So, if one of those numbers had been 7,
It
then
yeah.
it would have worked. So is there some guarantee that it will be S in the first one?
Sorry?
Is there some guarantee that this
No, it comes out that way. It comes out.
Just comes out that way.
It always comes out of the form S in resonance.
But are there solutions? Had there been a 7, would there be a good solution?
Well, not consistent with string perturbation theory because there are weird powers of tau.
No, but just in mathematics.
Yeah, sure.
There are
Oh yeah.
solutions to this equation with 7 and that.
Oh yeah. Even yes, they don't have to be even real. Just for the Riemann zeta. All you need is real part of the Riemann zeta is real part of S is to tell them. In fact, there are so-called, imagine there are so-called cusp forms which to the best of my knowledge even there are the closed form expression known for non-to mathematics. But these are much less understood these compared to say for example the like the holomorphic modular forms like the J function and so on. Because there is this theorem like that this G4 and G6 generates everything. The lowest two, but here there is a theorem.
What is it proof that it is always the SHS function and string
Sorry?
perturbation?
No, there's no proof, but it turns out that. Yes, it is quite clear. Okay, everything else.
And all the things that you verify, the homogeneous part will always have these numbers.
So that will depend on this thing, but they'll always will form asynchronous.
Yes.
It's quite nice. It comes out good.
Even when you go past the BPS case,
Yeah, yeah.
when you go to the derivative order, so it's not.
I'm going to tell you about 8 and 10 derivatives still works. Right. It is source of numbers. In fact, to the best of my knowledge, up to here was what this was a calculation due to Zagier. I mean, very different by direct sum. That is very tended. So calculation, the calculation is correct. So I'll give you the answer here because now I've told you about this. That is a very 1 minute thing, but let me give it to you. So this one is really E2. This one is and the normalization is 1, we just fix it for asymptotic analysis. This one actually is, this one could have been E3 plus a constant. And this turns out to be the constant is actually non-zero. I will fix the asymptotic analysis.
Asymptotic means large tau, small
Large tau.
So you compare with supergravity.
Well, this is also this is a worldsheet calculation. We just take this modular form and expand, take this graph and expand for last term. Right?
How do you know what the right answer is at large tau?
You know it because, for example, this one is a graph, right? You know this expression when you write it an infinite sum. Just make a last term.
No, but then you have to compare with what you know is the right answer at large tau too. And how do you know that?
No, I know this is a differential equation, right? So this equation I know.
No, you know that. So you get some homogeneous solution, and then you have to fix the normalization.
Right. Sorry. So here I know, for example, this equation will be solved by this is equal to some alpha times E3 plus beta. This one is the solution.
Okay.
So for leading order, I know this is going to be no. This is actually
Beta
twice
for-
beta things plus some tau to q plus beta. This one actually I can do the calculation.
Wait, how does constant solve that equation? 10 square constant is 0, but 6 on constant is
Oh,
1.
did I? You know, I think you're right. I got it.
Oh.
Sorry, yes, this one is still, this should be correct. Otherwise it would be easy to, thanks. So but now I see, now I can, but now I know this graph explicitly. Now I just make a last order expansion. Because what is this graph? I mean, you know, this is this sum, right? There is 3 of these sums. Like of this m tau plus n2. So that m1 plus m2 plus n3 is n3 is 0, m1 plus n2 plus n3 is 0.
So the second line
No,
that
wait,
you're
I
writing,
think alpha should be 1. If these two equations are true,
Which one?
then these two, right?
Right.
Then this
Ah,
alpha should be
yeah.
1. There can only
Sorry,
be
yeah,
beta.
right, yes. Yeah. Now that's it here. So now I fix beta from S&P. And here beta turns out to be nonsense. Because this you know how to calculate, right? It's complicated,
ah,
right?
In some way, yes.
sorry, I missed that. I'm sorry.
No, please go.
Okay, so you say that it's of this form. Now you need to know what beta is.
Exactly.
How did you fix what beta is?
Because I know how to expand this. Because what is this? This is really,
Wait, you say you expanded, but how, you have to know then what the right answer is.
yeah, but here I know what expansion is. Right?
So you've expanded it. You get, let's say you get 50. The constant term is 50.
Also
Then,
chemistry.
and then how do you know what beta should be then?
The beta is 50, right? That's what I said. Because see, what is this? This is really like an integral over the Green's function.
In addition to knowing the differential equation, he also has the exact expression as well.
Yes, this is
G1
G1.
has an exact. And then you compare with that exact expression. Thank you.
So I know it from here. Then it
Okay.
is simple.
So in the large tau 2 limit, you
I
can
can
compute the
just-
exact expression.
Exactly.
Thank
But
you.
the good news is just like one or two.
Okay, thank you.
That's much simpler than knowing
Thank you,
the
thank you.
exact answer. So this was a mistake here. Yeah, so this is what you get from this way. So I'm like doing other remaining ones.
And that is effectively just a supergravity calculation, right?
Which one?
The thing that you explicitly do.
No, because this is just taking this modular graph function and evaluating. Nothing to super.
But it would be the same as doing it in supergravity because you're doing it at very large tau.
So tau is the bullshit modulus of the this thing, right? Of the
Yes.
Doesn't it force you to low energy something?
oh yeah, it's in the sense because you're looking goes to the boundary of modulus.
Yes.
Right. So there's a couple of others left. This number 4. These are very simple. So now let me look at the somewhat more non-trivial ones because that is where the fun things are. So when you see that, I mean, it seems that this can't be done. Nothing what to do. So at D8 alpha there was a diagram like this. I actually could have had a diagram like this. I'll start with this. Here it doesn't matter, but I want to show that there's a relation between these two. So this one, I just want to show you some details of one simple calculation for others and give you the answer. So suppose I want to calculate the Laplace equation satisfied at this. So it's connecting 3 vertices with 4. So what is this? This thing on this. Okay, so whenever the del mu on a line, I just write it as mu on that line, just for relation simplicity. So I'll give you the answer. It is really twice the mu here and then mu bar here is this plus twice mu here and mu bar here. Let's trigger combination of this plus mu here, mu bar here. Plus 1. So now, let me evaluate one for it, at least one time. It's very simple. So let me see, the others are much more complicated, so the logic will be let me evaluate this one.
So also in some sense an entirely homogeneous equation. It's all the same graph.
Sorry.
Everything on the right hand side is the same graph as the thing that appears on the left hand side.
It's just
basically homogeneous.
It says mu and mu are sprinkled, so that there are no mu and mu on the same line. So it's very simple.
Yeah.
That's the whole.
So all the other guys also satisfy that property except for the one that you corrected, where somehow the nature of the graph itself changed. I mean, it was some G1 to whole cube or something like that. When you apply a Laplacian on that, it became a different diagram.
That was really a Poisson equation, not a Laplace equation. Because in the Heisenberg was 0. Exactly. So that was one of the not so simple cases, but compared to this complexity, that was trivial. So let me just work out this one because it's very simple. Also, in this answer a question, I will like how things work. But just for one simplest case. So suppose I'm evaluating this guy. So mu here and mu bar here. So I told you what is mu. It's equal to 1 by pi square. Again, everything is integral, so I'm not writing integrals. So mu actually brings in a tail here and the tail of this level. Mu bar brings the del bar here, the del bar here. Okay? So now what you do is just using momentum conservation move this del bar here. Right? So that just becomes this del bar. Okay? And I've told you delta bar is pi times this becomes delta function. So then this line is gone. You are left with this. The del here and the del bar here. Minus the one with these two removed, but there's a endpoint here that's 0. Right? That's simplification. Now to the same point, the del bar here is the momentum conservation. Right? So 1 by pi with another pi here. And again, these two guys come together.
You move that del bar by first moving into that leg and then moving it.
Exactly. Trivial integration. Yes. And now this one again is 1, so you shrink this to get this. And the other, when you remove this, is open-ended at 0. So it's both away. This is exactly equal to 3 over graph. So that adds 1 to the Heisenberg result. In fact, it adds plus 2. This is the simplest case, the others are more complicated. But I just want to show one example of how it is. So for this one, the right one answer is a bit more complicated. What will be? So that was the whole logic. Somehow use this because, I mean, if I were finding this differential equation, there's one whole paper actually with their wrote to review. Very, very complicated. But here's essentially the half of this. So I just, for these two, I'll give you the answer. Here I already told you. which iteration we made, it's essentially guess one. And the other one, if this one turns out to be real by itself, this is minus half. This thing. So now we'll add all the contribution. And what you get is delta minus 2. This is one of the and this is simple, this is really E2 square, this is E4. No step. So now I want to actually, this was simple. Now I want to consider another one which is kind of, yes, one more technically complicated. Because there's another
All the boxes cancel. No, it's not the boxes.
boxes. Yeah. So now I want to look at, sorry, it's clear. But collection will also be great.
And how will you solve this equation now? How will you solve
Yeah, I
it?
will never need to solve it actually when you do the amplitude. That's the whole point. Solving it was in back to the whole thing.
Okay.
So, yeah, I'll come to that. But let me just finish this block.
Yes.
So now let's look at this thing. Now you see problems arise. Because now if you do the same thing, okay, what you want to calculate is this guy. Mu here and the mu bar sum. So this is essentially, this is roughly like 2 dels here and 2 del bars here. Now you try to fill it out. We'll never be able to get del n and del bar on the same line pairwise to cancel. So it seems that you will left with some del and del. So it's, all the manipulations are not always completely trivial. So this was stuck with for a long time, and then I thought that, okay, then I introduced something called an auxiliary diagram to solve for these guys. Okay, so the point is, again, I guess the aim is never to give out this again, for the auxiliary diagram, I really don't have any constructive proof about constructivism. I'll just tell you, a guess which works. So I'll define the auxiliary diagram as the following. I start with a diagram which really trivially reduces to this. But the diagram should be, I should be able to independently calculate. Then equating these two expressions, I should be able to do this. So it's essentially producing by guess, just trial and error. So, so let me introduce an auxiliary diagram for you. So for this guy, I start with this diagram. This thing has a mu here, mu bar here, there's a L bar here, and a del here. So first, this del and del are in the same range, so that is trivial. So trivially, this is pi times, but this is strength, this is this diagram. This minus, because this is another pi, so these two open up, and you get this. And actually one can show, if there's an open split like this will be factorized. There's a trivial factor when you take this expression. This is not the difficult part. The difficult part is really this. So now in other words, if I can calculate this, modular understanding this, I can go. So can I calculate this? And here the thing is, this has two dels, this is a del bar, so then I can collide and hopefully things will simplify. And now, when I do this calculation, here's what I get. I get minus pi by 12, this thing, minus pi by 4, this thing, plus 2 by this thing, plus another complementary term. I'm just going to draw it. This is del, del, del. So these are going to figure out everything if I can calculate this guy. That doesn't look very promising. But for this one, I need to use another auxiliary diagram. Okay, so let me do it because this one step I wanted to give you some flavor before I even write any answers. Now here you see, nice, this is del and del on the same line. I think the same point, del bar del on the same point. So why don't you kind of make a surgery here and add a line here? That's the obvious case. So, so the diagram now I start with is this. There's a del here, del here. Del bar, there's a del bar here, and a del bar here. So now see there's one term which is trivial, which is this way. That is exactly what I want. And the another term is actually, because when it goes out, this is del on the, you can bring the two dels here, together. This is really mu here, mu bar. This is exactly like the kind which you had. Those are much more non-problematic. But this is, can you calculate this one exactly? By exactly removing all the derivatives. Here the answer turns out to be yes. That is give you the answer. This is minus pi cube this thing plus pi cube following that this thing mu bar minus twice mu bar so mostly there because now you see this is really mu this Laplacian acting on this soccer ball diagram kind of.
So just to see the powers of pi are coming because every time you apply del bar is equal to pi times delta function. Is that it? So we just contract it and we get pi.
So now we start with this. If you look at delta of this guy minus 3. This thing. The important thing is there will be a contribution here. Let me write it down for you. There will be a factor of 12 here, right? Trivial. Because the mu can act in 4 ways, the mu bar in 3 ways. This thing. Now act on this thing. You are going to get a minus 24 mu bar when they are acting on different and a minus 12 mu this thing. Because when mu and mu are acting on the same guy here, this is really E2. Right? Because again, this is del, move the 2 dels and the 2 dels. And you see this ratio is 2 here, minus 2. This is precisely this ratio. So as expected, this doesn't satisfy good Laplace equation by itself. It's this guy, it is connected, something connected. And this is exactly the number of ways we will chop this diagram in the reducible part. Because suppose you want to choose 2 of this, you would have chosen these 2 or these 2 or these 2. So we plug in this expression here, everything becomes very nice and you get a differential equation which is really delta minus 2 of this thing minus 3 of E2 square. Again, this is easy, so you know how to tackle it. This is the answer again. 26. This thing. This is at the end a very simple looking equation. So now, this one actually has eigenvalue 2. The earlier equation, that you once write it down, actually also an eigenvalue 2. It was 9, this thing. So this one actually will bring inside here with some number here, this satisfies an eigenvalue equation. So long as you can just eliminate these 2 terms. And that gives you delta minus 2. This thing minus 3, this thing minus 24, this thing plus this thing. Now again, you can use asymptotics because this is equal to 0 plus the function of E, number times E2. Again, that comes out to be 0. So you get an equation that this is really equal to this plus 3E2 square minus 15. So this is kind of a non-trivial, right here. Kind of a non-trivial relation between modular graph functions. These are source terms which are, essentially simpler in modular adjacency series. This is a highly this is kind of highly non-trivial relation between the modular graph functions because you wouldn't expect this kind of relation. These are the newer results. Some of the higher orders, I just write down the answer because then I just want to tell you.
So this kind of thing was not known from mathematics.
I don't know, perhaps I don't care or whatever, this was not. It seems that the interesting question and another generalization is that higher genus is really so, this is more of the sort of GH, R4 for D10, R4, I just quickly write down the answer. So then I want to tell you how to do the integrals and something we'll try to do for you. Just college to say. So, I'll just quickly write down the diagrams. On the D10 you have these are diagrams. This. So let me write down the equation that satisfies the answers. This one satisfies an easy equation. This is really 8 times this guy. This one is E5. So this is exactly like what we did before. Asymptotics tells you this 2/5 is fixed by this value. Plus zeta 5 effect. So if so, that's actually trivial.
constant you again compute by the large tower asymptotics.
Others, they satisfy some non-trivial differential equation, these four. I'm just not writing a differential equation, but I'll just write down the analogs of this equation which you get. Just to say something. The answer is the following. 40. So you can see how we can simplify. This. So you see, these are trivial. It's E2 times E3 and E5. So if you know this, you know this. So essentially, you can cross this one off from a list of independent ones. And if you just look at this one. And this one, the most complicated one, turns out to be so if you know this one, you know this one as well. So that is and finally, the last one is also wrong by the equation. Then this essentially is one. So it's a normal simplification and amplitude calculation. You will just all you have to do is just calculate. So now the point is how now that I know this Laplace equation, how do I calculate the finite part of the integral? That is why this simplification work. That's one reason why this integrals are not doable now. So the point is the following. You see, this very complicated graph function satisfy an equation something like this, right? This plus this. And what if it is this integral? d2 tau by tau square over f. So write it as d2 tau by tau square over f 1 by lambda of lambda f, which is box f minus the source. Now these are generally Eisenstein series up to this order. So this in principle you can give you the answer. So this is kind of doable. Now this one is not a boundary. So it's much easier. What is this? This is really integral d tau 1 from minus half to plus half del tau 2 of this f. That's tau del going to infinity. You have to keep only the finite. In other words, in f, all you need to know is the order tau. And then what? The coefficient is non-vanishing, it's a non-vanishing answer. Plus diverging terms which we cancel. So that is the reason why we never to solve this equation, because these are anyway not easy at all. So maybe I'll write down the answer for some of these expressions. What you get directly. So for r to the 4, you get 4 zeta 2. For t to the 4, r to the 0. For t to the 6, r to the 4 is 4. This was exactly based on S dual integral. And for t to the 8, r to the 4, the integral is a little bit. The integral actually had this guy. This thing 9, this thing plus 6, this thing plus this. So when you simplify, this just becomes half. Laplace acting on this guy minus 5. So this integral, this is also an Anirban equation. This integral can be done along based on what I told you. And the answer what you get is I square by 45. The important thing is what units of this integral. So that has to be done because it's straightforward because we know the expression of the Eisenstein series, but once to the integral. And the integral is not entirely trivial to give you the answer. So here we are doing Eisenstein series square, E2 square.
This d to the 8 was it non-supersymmetric?
No, non-supersymmetric. This is the first case where it's consistent. In fact, I will show you using a log L contribution, which tells you that from this infinite region there's a log S. So they must cancel. That's why I'm telling you the answer. So this is E2 square. Now if you naively try to do the logarithmic divergence, so what you do there is a calculation for ES prime. You take the limit S minus S prime go to 0. Because there's a cancellation. And the identity which you use, I just do the answer using the calculation by S plus now other terms which are polynomially diverging or polynomial is going to 0 as it goes to infinity. And by s as some complex expression is due by zeta is minus 1 gamma is half by zeta is and this log mu 2 is actually as an expressed expression is zeta prime us minus 1 by zeta is 1 minus zeta prime 2s by zeta 2s plus gamma prime as minus half by 2 half minus gamma prime s. So when you plug this one here, this gives you really minus 4 times square 45 essentially log L. So this gives you a finite term. But now this log L is a signal that when you do the other part which is left out, you get a contribution. This coefficient is uniquely fixed here, which is minus 4 pi square 45 zeta 3 log minus alpha prime s from mu hat. Log L must cancel when you add it. But this tells you that there is this infinite divergent term. This is a signal. And for the scale of denomination will change because in your mu here, you have to add. But anyway, that's the origin of seeing some of these infinite divergent terms in string coordinate theory. And so this is this thing, and there's this one more thing I wanted to say before you. So the point is, so far we looked at the
Sorry,
simplest.
I lost. Where did you first introduce this new things?
See what happens is this expression for ES is known.
Yeah.
ES prime is known. You write as ES times ES prime. You do the integrals. There's a 1 by s minus s prime term here.
Yes.
But there are numerators also will expand. Actually has some contribution. That gives you the law. There's some L to the s minus s prime.
No, the scale mu.
Yeah, the scale comes from the coefficient because when you actually when you take ES and expand, the coefficient involves various zeta function, the gamma function.
Okay.
So those also when you expand around s equals s prime, it comes some contribution.
I see. So you're just splitting s and s prime and
Exactly. There's a term like s minus s prime by s minus s prime something and function as s prime. So this one you really expand as in the usual way, 1 plus s minus s plus this thing. And this term is another contribution which is L s prime minus s. This one exactly cancels. And this also will write it this f this thing f log. So this one term cancels exactly. The coefficients are exactly opposite. But there's an order this term which actually gives you this log here. Because from here.
We got them such where mu.
where so are you saying that 1 plus s minus s prime log L
Exactly.
that is log L over b?
No. So the point is this one actually has an e to the log f. So there's this actually also has an s minus s prime. So this log L, there's a log f. In the limit with s equal to s prime.
What is mu in what you're
Log mu is defined here.
Yeah, log is defined.
Oh, it's just a number.
I'm sorry. It's just a number.
Yeah, it's in this. Oh, I should have just told you this. Yes, it's defined.
But this new hat here is more like the usual field theory, parameter.
The one thing is that string is uniquely fixed. So that because there's an issue. And you will calculate it what this is. So I'll just maybe take 2-3 more minutes. So the point is, so far we've been lucky because the diagrams only involve Green's functions. But no one ever tells you that involve only Green's functions. You can involve derivatives of Green's functions. So now I'll be telling you something about a 5-dimensional amplitude where derivatives of Green's functions come in. I'll tell you some later. I'll just give you the answer because the calculations are much more complicated. So the point is in the 5-dimensional amplitude up to d to the 6 up to the 5. Okay, this was calculation by Green, Mafra and Slaughter, this is a pure spinner. They actually showed that there were terms involving derivatives of Green's function, the derivatives could be removed. But the claim was that for d to the 8 r to the 5, d to the 10 r to the 5, I'm sure you also got in a higher order, I'm just looking at the two lowermost orders. There were certain diagrams which involve derivatives which are very difficult to remove very easily. So here there are actually two such diagrams. I just write draw them for you. This is the 5 diagram, the L here. So it's modeling in And this if you try to fill around with it, it's not very easy to get rid of derivatives. Because you have to get them there's another. And here there are 7 such graphs. If we draw them for just so we get an understanding of these things, and we get the bar. Was these graphs are on the basis of this diagram, they are supposed to be new limits of the basis because at this order, with this number of links, they are supposed to be new diagrams because we can't get it. But what I started was with, just by guesswork looking at auxiliary diagrams and trying to get rid of the limits. That is, for all these cases, derivatives can be unique. All these cases. And the normal simplification is that when you remove the derivatives, I just write down the answer for one or two. They are expressed in terms of graph function without derivatives, most of the kind which I already talked about. And certain new ones, but all of them will satisfy some Poisson equation. So then the phi graviton is also solved. So the answer is right now for this first 3 diagrams, that will be it. So here's the answer. It just doesn't keep playing around and getting the correct auxiliary diagram. It's complicated, but everything is known. Much more straightforward. Then we have this one. See, at least for D8 alpha, I've given the answers for both. So D10 alpha is the right one answer for both. Others are not so complicated. So, this is our thing. And of course, some of them are 6 vertices. For example, this is these 6. But in principle, you can find Laplace equation for all. For example, like, as a random one simple equation between 6 vertices, which is not at all obvious, which I thought, which was this so-called Mercedes diagram. This can be So this generally helps in enormously simplifying the calculation because now this will be Poisson equation is the local is the modular modulus is the negative rate. So this is some recent progress I made on understanding at least one loop amplitudes. I mean, clearly this is really the starting point when it is going beyond what I told you.
But I think it's questions. Right. Okay, this Laplace equation was very important to you. So I was wondering, in the case of the open string, where for just like a real model, right, is there anything analogous to it?
Yeah, should be. People haven't nothing. Beyond what I told you, really nothing is known in the equation.
But do you think that there is what could play the role of the Laplace equation?
Yeah, there won't be SL2Z invariant, but there will be some t parameter. There should be some equation for that. We should recommend
like del G squared, just
exactly.
so one dimensional. Just following up on that, if one wanted to do the calculation for D3 brains, we know that S matrices in N equals 4 angles have these fantastic properties. A lot is known about them just in field. Now you could wonder properties lift to
Right, exactly.
S matrices of D3 branes in the string theory.
Must be like that.
And I was wondering whether you could make some connections between the way you're thinking here and the extensive work on S matrices in the quantum field theory.
And that will be, this will be really going beyond plane.
Yes.
So I mean, yeah, a lot of things should be possible. I just, this is the kind of the first things I tried. Because I mean, initially it looked very simple, but then before I got this auxiliary diagram, apart from one or two diagrams, I couldn't solve anything.
Right.
Then it was after, then come up to that this helps, and then these things simplify. I'm trying to look at even some simplest things, this is super simplest stuff like that. Because really, beyond what I told you, really nothing is known. These things have been generalized. Grover and Clady have a paper where they kind of draw the analogs of these diagrams up to with 6 links and so on. But that's where it ends. And there's all kind of relation between these diagrams and so-called elliptic polylogarithms and so on. And in mathematicians they call modular identities which result from these things. Because when I wrote down the lattice sum, this 1 by m over n square, that's what's called the Kronecker Eisenstein series. And they have this, you can take this Kronecker Eisenstein series naturally here, and they make a Fourier transform of that. Those are what are called these Wigner Ramakrishnan polynomials, block Wigner Ramakrishnan polynomials. So these are non-trivial identities between polynomials, which are generally quite hard to explain. So there's been all kind of this thing, but beyond what I told in string perturbation theory, so far nothing has been done. Nothing can be done.
So something like this heat equation is satisfied by higher genus theta functions also, is it? I mean, I just don't know about that.
Not quite, because for example in higher genus, when you actually have something like this, the endpoint doesn't vanish anymore. The zero mode matrix. Because in code as the translation of zero mode trivial decomposed. Essentially the Bertrand differential is globally, you can define it. But in higher genus it doesn't matter. In fact, in the higher genus, the only analog of that is known. In higher genus, for the d to the 6 r to the 4, this is an integral of this genus to modular space. Okay, and the d to the 6 r to the 4 actually has just this. And this one is what's called in mathematics the Gauss-Mizan invariant. This actually satisfies Laplace equation and this. So now you actually can do the same trick here. This one localizes on the boundary of modulus because there is a separating node and a non-separating node. This one is contributions only from the separating node. So this is a pole here. That helps you if you solve this thing. But to higher this thing, I've been told that I was thinking of this Green's function techniques might be useful. That I was told that in the Doppler and Doppler and Green are trying to work out this higher numbers. So I mean, just thinking first to see what they get. The structure is very different. But surely this should be doable. I mean, it's always doing higher numbers. Nothing has been done.
Sorry, one more question, only tangentially related to your talk. I believe Strominger was here last week. He was telling us one of the things he mentioned was that he was talking about the infrared structure of gravitational scattering amplitudes in 4 dimensions. And in 4 dimensions, there's this problem that gravity amplitudes aren't really well defined.
Okay, infrared
differences. Is it right that in 5 and higher dimensions?
Yes, infrared doesn't should go away.
Go away. So there is
even at one loop and higher loops, one perhaps should be able to get a universal view.
Yeah, so there is a well-defined amplitude that will obey well-defined unitarity relations. But that is not true for
Exactly.